the receiver's state is the standard basis or in the Hadamard basis. Okay. In fact, this is a special case of a kind of a more general framework that was introduced in this work from 2019 of Koji Kaoru et al. They call this particular instantiation of malicious four states Q factory with basis blindness. So maybe you can see where this basis blindness notion comes from. But we basically abstract out this idea of OSP and kind of study it in its own right. Okay. And one thing I also want to note is, again, if you've seen kind of work on remote state preparation, often the security property is a bit more involved, and it's asking for something like simulation security or some verification verifiability property. And here we don't require anything of the sort. Our security property is just kind of this simple indistinguishability based security. Okay. And then I should mention that we also consider, in particular, like a round optimal version of OSP, which is 2 rounds. So here, actually, the sender has to choose the bit, the choice of basis beforehand, and kind of use it to prepare its first round message. And if you think of it, you can see that basically this is round optimal, and there's no way to do just a 1 round OSP protocol satisfying correctness and security. Okay. Good. So, we study this cryptographic primitive, and we have a few kind of different types of results. So first, we show that, it's instantiable from cryptography that's been quite useful recently in designing kind of classical client quantum server protocols. So in particular, we show that trapdoor claw-free functions imply OSP. And the interesting thing here is that we don't require any kind of extra properties like an adaptive hardcore bit or something like this. So we call this just a plain TCF. Okay. If we do add the dual mode property, we can achieve just this round optimal two round version of OSP. And then from the literature, we have 2 different ways of instantiating TCFs from different kind of flavors of cryptographic hardness. One is from LWE, and another is from hard problems on group actions. Okay. Good. We also, the way I presented OSP so far is I talked about, preparing a state in the standard Hadamard basis. It's pretty natural to imagine, a choice of any 2 bases, maybe 2 bases that are not quite at a 45-degree angle. And so we have some results about studying the relationship between, OSP for these different pairs of bases. Okay. So another class of results we have is on, the power of OSP. What can we build from just OSP without any other assumptions? So we can use it to generically build proofs of quantumness and even anti-commutation tests, or tests sometimes called tests for a qubit. We show that you can just generically use OSP to blindly delegate arbitrary or classically delegate arbitrary quantum computation. And in turn, we show that this actually implies the ability to classically verify BQP quantum computation. Okay. If we have the 2 round version, we can achieve something that has been formalized in previous work called a 1 of 2 puzzle, which itself has various applications. So quantum money with classical communication, basically preparing unclonable states with classical communication, as well as classically verifiable position verification. And then if we add classical FHE, so FHE for classical computation, we can achieve quantum FHE. Okay. So, given the fact that OSP seems to be a pretty powerful primitive in its own right and has all these applications, and on the other hand can be built from TCFs, we'd want to understand actually what sort of cryptography is necessary for building OSP, right? Can we possibly do it from something weaker than TCFs? Maybe even something like a random oracle, right? So we show that this is unlikely by demonstrating that OSP, again, without any additional assumptions, implies a classical communication oblivious transfer protocol, okay, between one classical, one quantum party. And then, if we have the 2 round version, we can actually get a public key encryption scheme with classical keys and ciphertext. And this certainly provides evidence that it is difficult or perhaps impossible to build OSP from just something like a random oracle. Okay. And then I wanted to mention that actually after our work, so a very recent work also showed a 3rd instantiation of OSP from a lattice isomorphism problem. So this gives like another potential source of cryptographic hardness from which we can build all of these applications. Okay. All right. So, some of the main takeaways so far that I want to emphasize is essentially this, OSP is this simple but seemingly quite powerful primitive that unifies a lot of these constructions, previously, somewhat complex or ad hoc constructions in the classical client quantum server setting. And, by kind of abstracting out this primitive and studying it, we've been able to show a few even new implications. For example, this implication to quantum money with classical communication from TCFs, like without this adaptive hardcore bit property, was not known before. And then these implications to blind and classical verification of quantum computation just from plain TCFs is also new. Although this is actually concurrent with two works, one of which was at ITCS earlier this year, and one of which you'll be hearing about right after this talk. And interestingly, kind of all three of these works kind of approach this problem in quite different ways. But we all end up showing that basically you don't need, you can build these like verification protocols from just plain trapdoor clock functions. Okay. So for the remainder of the talk, the last few minutes, I just wanted to go into some detail about, how we use OSP to build some applications. I want to cover, how we use it to build a so-called computational bell test and some applications of that. And then I'll get into, how we use it to build cryptography, build like structured cryptography, like public key encryption, which kind of gives lower bounds on the cryptography needed to construct OSP. And there's a large part of our paper that is dedicated to the applications to blind and verifiable quantum computation, but due to time constraints, I'll let you see the paper for that. And then also the talk after mine should be, giving some information basically about how to, achieve these applications using a slightly different approach from us, but it still will be somewhat similar. Okay. Okay, good. So start with proofs of quantumness from OSP. And we do this via this, computational bell test. Okay, so hopefully you'll see what I mean by this fairly soon. Here we just have a quantum prover trying to convince a classical verifier that they're doing something quantum. Okay. So to do so, the verifier will just sample a random bit and kind of input this to an OSP, and use this OSP to prepare a BB84 state on the prover's side. And again, here the bit now X determines which basis the prover receives. Okay. So now the observation, which is has been present in several prior works, is simply that the prover's state at the end of OSP, this BB84 state, is exactly the same as Bob's state in the CHSH game. Okay, after Alice answers her question X with answer A, right? So recall that Alice and Bob share an EPR pair. If Alice is asked X equals 0, she'll measure her half in the standard basis. And if it's X equals 1, she'll measure her half in the Hadamard basis, and Bob's state will collapse accordingly, right? So we can see that, if X equals 0, Bob/prover's state is the standard basis, otherwise it's in the Hadamard basis. So the idea behind this, and some of these previous works, is just to simply complete the CHSH game with this prover. The verifier samples Bob's question, and the prover will just implement Bob's strategy. So if Y equals 0, measure his state in the X plus Z basis. Y equals 1, measure it in the X minus Z basis, and return the resulting bit. And the verifier will accept if the CHSH predicate is satisfied. Okay. So this is the proof of quantumness. And you can show that by the CHSH strategy gives us a completeness of at least 0.85. And now we want to show how to basically reduce the classical soundness of this protocol to the security, kind of directly to the security of OSP, right? So this is how that goes. Suppose we have a classical prover that succeeds with probability non-negligibly greater than 3/4 in this protocol. Let me actually just rewrite this verification predicate as, accepting if B is equal to A XOR X dot Y. And the idea is very simple. So let's just record what the accepting bits are for the two possible verifier challenges, right? So if Y equals 0, the accepting bit from the prover is just equal to A. If Y equals 1, the accepting bit is just equal to A XOR X. And so the idea is that, if I have both of these accepting bits, I can just XOR them together to get X. And X is exactly the bit that's supposed to be hidden due to the security of the OSP, right? So the idea is that if the prover is classical and they're succeeding with probability greater than 3/4 by a simple rewinding argument, we can show that you can obtain both accepting B0 and B1 with probability non-negligibly greater than 1/2, which implies that this prover would then be able to predict this bit X with probability non-negligibly greater than 1/2 and violate the security of OSP. So this gives a very kind of straightforward reduction to the security of OSP. Good. So we can actually take this template is quite versatile, and we can use this to show like tests of a qubit following this previous work of BGKPV. And we can even show additional properties such as the following. Even if we have a quantum prover, they can win the CHSH game with probability 0.85. But you can show that they shouldn't be able to clone the state that results from OSP, because doing this would also allow them to answer both verifiers' challenges with too high of a probability. So by kind of playing with this property, we can obtain quantum money and applications to position verification as well. Okay. All right. So let me move on and and spend a couple of minutes on how we derive public key encryption from actually the 2-round version of OSP. And here we actually first use 2-round OSP to give us what I'll call a 2-round encrypted CNOT protocol, and then use this to get public key encryption. Okay, so how does this work? Well, an encrypted CNOT is a protocol between a classical client on input B and a quantum server, which has as input some quantum state. They communicate classically, and at the end, the server should have either applied CNOT to their state or have done nothing to their state, depending on the client's input B. But of course, this will be kind of encrypted under a one-time pad where the keys are known to the client. So we kind of need to keep this hidden from the server because, again, the key security property is that the server shouldn't know if they've applied CNOT to their state. Okay. This is a primitive that was introduced by Mahadev in 2018 as a building block for QFHE, but we kind of study it in its own right in this paper. And in particular, again, we consider this kind of 2-round version of the protocol, okay, where the first round message depends on B, and the client maintains kind of a secret state after generating this first round message, which they then use to derive the one-time pad keys. Okay. So this will be kind of a very brief proof by picture, basically. But how do we go from OSP to an encrypted CNOT? Well, here's a basic idea. I don't expect you to just completely parse this, but this is a circuit which just consists of some CNOT gates and some measurements. And you can confirm that if I apply this to some state psi, as well as these two auxiliary states, plus and 0, at the end I'll get a CNOT applied to psi up to some one-time pad. Okay. The idea is that if I apply the exact same circuit, but I switch these two auxiliary states, so instead of initializing plus 0, I initialize 0 plus, then it turns out that I apply nothing to psi. Okay. And so this is exactly what OSP allows us to prepare, right? I can send to the prover either a plus followed by a 0 state or a 0 followed by a plus state, and the prover can't tell which I did due to the security of OSP. And if the prover applies this circuit, then this exactly gives us an encrypted CNOT. They can't tell whether at the end of the day they've actually applied the CNOT or not. Okay. This is a very high level of how we get the encrypted CNOT. Now, finally, to complete our construction, here's how we get a public key encryption from this primitive, right? So let me sample a random bit R. Let me use this random bit to generate an encrypted CNOT first round message, which is the public key, and then the secret key is just the remaining state, okay? To encrypt a bit M, I'll prepare a plus and a 0 state. I'll apply the encrypted CNOT to this state, and so I'll get a 0, 0 plus 1R up to some one-time pad. And then let me just rewrite the state for convenience. So this is equal to 0x0 plus 1x1 up to some phase, where x0, xor, x1 is equal to R. And I'll have the encryptor just measure this to get some bit B and a bit xB. And the ciphertext will consist of kind of the second round message, the bit B, and then they'll mask your bit M with x sub B. So decrypting is straightforward. If you know the state for the encrypted CNOT protocol, you know the description of this state that was prepared. You can recover x sub B, and then you could recover the message. So very briefly, security basically relies on the following intuition, right? If I'm just kind of like an eavesdropper and I'm observing the public key, observing the ciphertext, and I'm able to predict the bit M with good probability, then over the random choice of B, I should be able to predict XB with good probability. Okay, and so this gives me this means that I should be able to predict both X0 and X1 simultaneously with some good probability. And again, that by XORing these two together, that exactly allows me to distinguish this bit R, which again is the bit that should be hidden by the encrypted C0. So we get a nice kind of direct reduction from the security of this public key encryption scheme to the indistinguishability property of the encrypted C0. Okay. So and also see the paper for an implication to also oblivious transfer. So let me wrap up. I think there's a few open directions that you could go. One is like more applications of OSP. I mean, we worked out several applications, but there are some that seem a little bit trickier. Actually, some applications in classical communication, quantum cryptography, for example, like certified deletion or vocal crypto, we did not know how to derive from OSP. There's a very interesting question, like what else actually implies OSP? Because OSP implies so many applications, it's interesting to try to understand what else we can build it from. And one really interesting question is whether we can instantiate it based on coding-based assumptions. Okay, and then there's some other you can try to understand if like other kind of generic primitives imply OSP. And then I think there's various ways that we can continue studying OSP as a basic cryptographic primitive and try to kind of understand better how OSP behaves as a primitive. Okay, and so yeah, that's what I wanted to say. Thanks a lot.
Okay, we have time for 1 or 2 questions. Okay, maybe I'll ask a basic question. So you have a result showing epsilon OSP implies OSP. Have you thought about the other direction, whether you can use OSP to build a...
Yeah, actually that we did leave the other direction open. Yeah, ideally we would want to show that OSP for any angle basically are equivalent, but there's still some gaps there. Yeah.
We don't know how to do the other direction.
Yeah.
Okay, let's thank the speaker again. Okay, so the next talk is going to be compile non-local games from any trapdoor claw-free function, and Kanye is going to give the talk.
Thank you very much for the introduction. So, I will talk about compiled non-local games from any trapdoor claw-free function. This is a joint work with my former colleagues Alexander Kolbe, Giulio Malavolta, Simon Schmidt, and Michael Weiter. So the setting in our work is the following. On the left-hand side, we have a non-local game. For now, what you have to know is only that a non-local game is nothing else but a game between a verifier, which we also call a referee, at the top, playing against 2 provers, which we also call players, Alice and Bob in this case. And what the players try to achieve is to maximizing their winning probability of winning this game. In the middle, we have a compiler, which is nothing else but a transformation, which takes a non-local game as an input and outputs a so-called compiled non-local game, which is again nothing else but an interaction between a classical verifier and some prover And in contrast to the non-local game, we only have one prover now. And ideally, if we have such a compiler, we would like to preserve some properties of the non-local game in the compiled game. Otherwise, you can define anything as a compiler and you will not get any useful application out of it. So for those who are not familiar with non-local games, let us take a brief look into a specific non-local game, which is maybe even the most well-known non-local game, called the CHSH game, named after the inventors Clauser, Hornig, Shimoni, and Holt. In this game, the referee is sampling two questions, X and Y, which are bits. And another crucial assumption in non-local games is that during the execution of the game, the two players are not allowed to communicate with each other. However, they are allowed to meet beforehand and agree on strategy, trying to maximizing their winning probability. So after receiving those two questions, they will locally compute something and come up with two answers. Alice will send over A to the referee and Bob will send over B to the referee. In the very end, the referee will see if the winning condition is satisfied. In this specific game, it means A, X, or B should be equal to X times Y. Or in other words, on the right-hand side, we can see the table. If X or Y equals 0, the two answers should be the same. If X and Y both are equal to 1, the two answers should be distinct. Now, when considering non-local games, we are usually interested in the so-called classical value, which is nothing else but the maximal winning probability for classical players, and also the quantum value, which is the maximum winning probability for quantum players. Now, for the CHSH game, one can show that the classical value is exactly 75%. This means we can find a classical strategy for both classical players so that they win with a probability of 75%, but also any kind of other strategy, even randomized strategies, don't exceed those 75%. In contrast, the quantum value is around 85%, meaning we can again find a quantum strategy where the winning probability is around 85%, and you can also show that this is the best possible strategy. And let's pause for a moment and see the consequence of this. So if the referee is playing against two players, he can observe what the winning probability is in the very end after doing a lot of runs of this game. If the referee is seeing that the winning probability is above 75%, he can for sure say that both players are non-classical. That's also the reason why we can say this is a two-prover proof of quantumness. Now let's take a closer look at a compiler. And again, I want to emphasize that the compiler should preserve somehow some properties of the non-local game. Ideally, the winning probability for classical players in the compiled non-local game should be the same as in the non-local game. Same for the quantum value. The first such compiler was proposed by Carlyle, Lombardi, by Quintanofan and Yang, which relies on the assumption that a quantum homomorphic encryption scheme exists. And the basic idea behind that compiler is to play the game on the to play the non-local game in a sequential way, meaning we will send over first the question X, will receive the answer A, send over the question Y, and receive the answer B. However, we have to encrypt the first question and get an encrypted answer. The reason is that from that we can get nicer properties from the compiler. And those are the two properties which were shown in the initial paper. The first property is the so-called quantum completeness, meaning whenever you have a quantum strategy in the non-local game, you can compile it to a new strategy in the compiled game such that the winning probability in the compiled game is not decreasing. So it is exactly the same or above it, plus some negligible term here. And for classical soundness, they showed that the classical value in the compiled game is at most the classical value in the non-local game. So let's pause again for a moment here and see what the implications are of this. Assume we have a non-local game where the quantum value is a little bit higher as the classical value. Then this gap is also preserved in the compiled game, meaning we will get a proof of quantumness where we only have one prover. Now, subsequent work also showed different properties, the so-called quantum soundness, which means that the quantum value in the compiled game is upper bounded by a so-called quantum commuting operator value, which I didn't define and will not, but we also have similar results for that. And in the NZ paper, they also showed some rigidity results with respect to the compiled CHSH game. Out of that, they constructed new classical verification of quantum computation protocols. And both of them under the assumption that we have a quantum homomorphic encryption scheme. Now let's take a look at our compiler. The basic idea is very simple. So on the upper right, you can see the compiler by Kalai et al., where they use an encryption for the first question and get back an encrypted answer. However, quantum homomorphic encryption can be thought of as a minimal blind classical computation delegation here, since you are only sending over one question and getting one question back. So we could try to abstract this away and come up with a interactive blind classical delegation instead of a QFHE, which is also what we do later. And to construct that blind classical delegation, we will use some modification of the so-called UBQC protocol by Broadbent, Fitzsimons, and Kashefi, which was proposed in the measurement-based quantum computation model as opposed to the quantum circuit model. And a note on that is that in that protocol, the verifier is allowed to send qubits. So we have a quantum communication happening in that protocol. To replace that quantum communication with a classical communication, we'll come up with a new blind remote state preparation protocol to replace that quantum communication. Okay, let's first take a look at our half-blind quantum computation protocol, which is a generalized UBQC protocol, I said earlier. Again, the verifier can prepare single qubit states in the following. So those states are called the rotated cat plus states, which is just the cat plus state with a relative phase to it. In this case, we have 8 different angles, all multiples of pi over 4. And these states are nothing else but those states in the XY plane of the Bloch sphere, as illustrated in the upper right illustration. Now, I will not go into details for our HBQC protocol, but I will tell you a little bit about the mechanics, and on the next slide also what happens in the middle of the interaction here. So what we have here is the following. The prover has a quantum state, cat psi, and the verifier has a classical description of the unitary that the verifier wants to apply to that quantum state. And after a lot of communication, we have the following outputs. The prover holds the quantum state U prime tensor I applied to cat psi, where U prime is our initial unitary we want to apply, concatenated with a quantum 1 pipette. And the verifier has a classical description of that quantum state, meaning he has all the quantum keys here, quantum 1 pipette keys. Regarding security, what we can show is that the prover will gain no information about you and the quantum 1 pipette keys. However, I'm lying a little bit here. The prover is knowing the dimension of U, since he has to know on how many qubits U has to be applied to. And the whole point about this is that the protocol holds unconditionally. So we didn't introduce any computational assumption. The only assumption was that the verifier can prepare those qubits and send it over, which we are trying to get rid of later. So regarding the HBQC protocol, in the first step, what we do is the so-called state preparation phase. V will sample a lot of quantum state, rotated cat plus states, and send all of them over to P. P will now construct the so-called brickwork state, where the blue circles correspond to the quantum state cat psi and the white circles to the qubits sent by the verifier. And the edges in between those are nothing else but control Z operators between those qubits. Now P is preparing exactly this quantum state. And the verifier will now we'll go to the next step, which is the computation phase. And the computation phase only consists of classical interaction. So V is saying that the prover should measure a specific qubit in a specific basis, and the prover will do it and transmit the result to the verifier. This will go back and forth until we measured all those qubits in the red box, so that we are left with those qubits in the very last layer and also on the first layer, which do not belong to the brickwork state. And those qubits are now in the desired quantum state. So that was our HPQC protocol. The main takeaway is here that the classical verifier can blindly operate on a quantum state held by the server. Now we are trying to get rid of the quantum communication by using a blind RSP. For those who are not familiar with RSPs, an RSP allows a classical client to delegate the preparation of the single qubit state to a quantum server without revealing any information about the quantum state. In our case, we are preparing a blind RSP for those 8 states here. And to construct this, we rely, like in the previous talk, on a post-quantum secure cryptography function. For those who are also not familiar with TCFs, a TCF is nothing else but a family of injective function pairs, F0 and F1, with the same image, where we also have the claw-freeness property, meaning for any QPT algorithm, it is infeasible to find the claw X0 and X1, such that if we apply the corresponding TCF to it, we get the same result. So same image there. However, if we are giving a trapdoor and some Y in the image, we can efficiently invert it to compute a claw X0 and X1, mapping to that Y. Okay, let's take a closer look at our blind RSP. Before explaining the whole protocol, I'll explain a subroutine which we are using in our blind RSP, which is parameterized by some natural number n and some quantum state, one single qubit quantum state holding by an prover. So V will just sample those TCFs, will send over n and the TCF. P will take his quantum state, cap psi, entangle it with a superposition over all possible bits, will apply the TCF coherently, measure the last register, and will end up with a claw state right there. Now he's sending over the measurement result. So since V has a trapdoor, he can efficiently invert Y to get those 2 pre-images. So now V has a description, or more or less a description of the quantum state. Now we will sample some random strings to incorporate some Goldreich-Levin theorem in the very end to get our security result. We will send over that. The prover will do a lot of computations here until we are ending up with the same state, but added some relative phase. In this case, -1 to the power d times x0, xr, x1, and some omega n to the power, what is written here? The takeaway here is that V has a classical description of that relative phase we added to that quantum state. Now our blind RSP is relatively simple. We will just execute the subroutine 3 times in a row with different parameters. We are starting with n equal 2 and cat plus. After that, we will take n equals 4 and cat 1, where cat 1 is the output of the previous subroutine. We'll repeat it a last time with n equals 8 and the output of the last subroutine, so that the prover is ending up with cat 3, exactly our desired quantum state. And security says that from the prover's perspective, or from the prover's point of view, theta is uniformly random. So all in all, what we have is we constructed a so-called half-line quantum computation, which is nothing else but a generalized UBQC protocol. We constructed a new blind RSP protocol for those 8 states under the assumption that TCFs exist. We combined those 2 protocols to create a classical blind delegation of quantum computation. And that classical blind delegation is then used to construct our new compiler. In the paper, we also showed that you have the 2 properties, quantum completeness and quantum soundness, and also some rigidity result. And in the very end, we extended Mahadev's result from a specific TCF from LW implies classical verification of quantum computation to any TCF implies a CVQC, like our previous speaker. And that's it. Thank you very much.
We have time for a few questions. Okay, tough crowd. Okay, maybe I'll ask a question.
Sure.
For quantum soundness slide,
Yeah.
you mentioned that I guess my first question is your compile protocol achieve soundness like the commuting operator value plus negligible?
Exactly. We have exactly the same results as before.
Okay, and do you have an explanation, maybe simple one, why we get the commuting operator value rather than the quantum value?
I mean, that's another paper, which also from my colleagues I'm not familiar with, but I think it's very hard to show that currently we are not sure. So let me go back. Currently, we are not sure if we can even show something like that. So we only know that the upper bound currently is this quantum commuting operator. I'm not sure why the techniques they use are not possible to use for getting an upper bound by the quantum value.
And you're using roughly the same thing as there.
Exactly, we're just leveraging all the results from there.
I see, thanks. Any other questions?
That's kind of, so I guess the point is instead of having quantum FHE to have claw-free, that's the.
Exactly.
Okay.
So the whole point's about constructing a new compiler from new assumptions. And as we saw, we have new results. For example, that the TCF implies classical verification of quantum computation.
Oh,
So arguably the point is a little bit more than that, right? You're factoring the CVQC protocol into a clean protocol, information theoretic protocol, where the verifier sends a little bit of quantum states and then compiling it with RSP,
That's
right?
what
This is a
we
very
did,
general
right?
methodology
Yeah.
that, yeah.
okay, so I think that's, we'll prepare for the next talk. Thanks to Kanur again. Okay, so our final talk is going to be on quantum one-time protection of any randomized algorithm. And Sam is going to give the talk.
Hi, yeah. So I'm Sam Gunn, and I'm going to be talking about quantum one-time programs. Okay, so what is a one-time program? So imagine a setting where Bob over here has some proprietary software that he spent a lot of effort to build. So maybe it's like a video game, or this is like supposed to represent like an optimization algorithm, or maybe it's like an AI. Okay, so he wants to be able to give Alice access to this software, but he doesn't want to just give Alice all the code because the code is really valuable. He wants to just let Alice have the ability to run the code. Okay. So what I mean by that is, at some point later in the future, Alice should be able to take any input. So in the case of this is like a protected AI, Alice should be able to, give any input to the protected thing she has, and then get an answer. So maybe it's like something like this. And just kidding, that's not real. But and then okay, the key point is that this thing should be useless afterwards. So the moment that she gets one response from it, it should self-destruct. She should never be able to get another useful answer out of the thing again. Okay, so unfortunately, this is obviously impossible with classical information alone. The reason is that Alice could just take whatever bits Bob sends her and then just clone them as many times as she wants and then use the thing any number of times in the future. Okay, so this is clearly impossible with classical information. So work of Goldwasser, Kalai, and Rothblum show that that using hardware assumptions, you can achieve these with classical information. But the purpose of this talk is going to be to try to use quantum information to have no hardware assumptions, just do it outright. Okay, so unfortunately, it's still impossible to do in general. It's still impossible to one-time protect arbitrary programs, even with quantum information. And okay, so why is that? Let's see. It's really, really simple. So suppose that Alice has some input X that we want to compute on, and then say that psi is like the one-time program token. Okay, so if you have one of these, say that you have there's some procedure for combining these things to compute an output of the function. So do that, whatever that is. Do it in a purified way. So that's why I'm writing a unitary here, and then measure the output. So f of x, and then just uncompute. So if f is a deterministic function, if you're trying to compute any deterministic function, then you can just measure without disturbing the state. And then after you do all this, you'll end up back with the token. You didn't change anything. You can keep using it. Okay, so the obvious question is, what if f is randomized, right? What if there's entropy in the output even for a fixed input? So okay, you might think like, oh, does that matter though? Is that like a contrived setting? But I would argue that actually, all three of the settings that I motivated with on the previous slide, I think it's actually pretty natural to think that it might be randomized. So like maybe the video game has like stochastic behavior in it. Maybe the optimization problem has many solutions and you get one of them. The AIs just natively give you random outputs. So for all of these things, it's actually not crazy to require randomized, to use randomized programs. Okay, so before we get in a couple of slides, I'm going to show you a construction for general purpose, like one-time protection of arbitrary programs in a strong oracle model. But before I get to that, let's talk about older work of Ben David and Satath, where they show how to one-time protect a very particular function, which is like a signature function for a signature scheme. Okay, so here Bob is going to send the program token, which in this case is like what we'll call a signature token. It'll allow Alice to sign just one message, and then at any point in the future, Alice can take her input, which is a message, use the token to produce a signature of the message. And then, the key point is she shouldn't be able to sign more messages than the number of tokens that she had. Okay, so this is, yeah. So I'm calling it one-time authentication here because for the purposes of this talk, it's gonna be fine for us if our authentication algorithm, if the verification for this signature requires a secret key. So it's like a one-time signatures, except that the verifier can require the key. So, oh, okay, I updated this, but yeah. There should be a verify of the signature here. Okay. So turns out it's really easy to build one-time authentication schemes. So let me show you this construction, and then we'll get to, on the next slide, we'll show how to, or on the next couple of slides, we'll show how to use this one-time authentication scheme to build one-time programs for general purpose algorithm. Okay, so turns out that, to construct this, it's very simple. The token can actually just be what we call a subspace state. So this is just a uniform superposition over like a linear subspace of f2 to the n, like a random linear subspace of f2 to the n. Okay, so the key fact about the subspace states is that if you Hadamard all the qubits, you get a uniform superposition over the orthogonal subspace. So Ben David and Satath say, well, if you have one of these, you can use this to sign as like a one-time signature token for 1 bit, because if I want to sign 0, I'll just measure this. If I want to sign 1, I'll just Hadamard and then measure this. And then they show that if I get just one of these token states, I can't produce both something in the subspace and something in the orthogonal subspace. So this is why it's like a one-time thing. And because we don't require like public verification for our work, you don't even need to do anything else. Like the description of the key is just a description of the subspace. Okay. Okay, so with one-time authentication tokens in hand, we can try to, there's now like I think a pretty natural way that you might attempt to build one-time protection for arbitrary programs. So this is going to fail, but let me show you maybe the first obvious thing that you might think about. So Bob wants to protect some function f where input is x, but now there's some randomness r. So what he's going to do is he's going to publish a program token that's going to consist of two parts. So first, it'll be just a one-time authentication token, so like a subspace state would suffice. And then second, it's going to be an obfuscated program where the program does the following. So the program takes the input, the randomness, and purported signature, verifies the signature for the input. And then if the signature is valid, then it's just going to compute the function with the given randomness. Right, so this is, I think, the most natural thing to do. It's like, well, look, the user can only sign one thing, so it seems like you can only evaluate this program on one message. Okay, and then the obfuscation is going to protect you from just looking in at the code and seeing the code for F, right? Okay. Oh yeah, so here it's just some arbitrary obfuscator, but for security, we're gonna model the obfuscator as a black box obfuscation. Okay. So yeah, so I already described how to evaluate. You just sign your input and then apply p hat. Okay, but the problem with this is that, well, this function, the function that takes x in R to f of x in R, is completely deterministic. So actually, if Alice just, instead of actually measuring using the token to get a measured like signature of her input and then computing with that, if she just does the whole thing coherently, then measures the output of f, then she won't disturb anything. So so there's actually nothing stopping Alice from just using this token as many times as she wants, with what we just described. Sort of the problem is there's nothing to force her to actually measure the signature. Okay. So here's our actual construction. It's almost the same, but now instead of letting the user sort of specify the randomness, we're going to generate the randomness as a hash applied to the input and the signature. So this hash function will model as a random oracle for our security proof. Yeah. So now to evaluate, you just sign your input and then compute this p hat. Okay. Yeah. So okay. Before I get into I'm about to show you like sort of some security analysis for like some limited notion of security. But first, I want to just point out a few nice features of this construction. So the first thing is that the quantum requirements are completely independent of the program that you're protecting. So you might say like, this is but this is totally impractical, right? Because if you want to run this with like an optimizer or a video game, then you need to load your whole video game on a quantum computer. But that's actually not even true. All you need to do is store like a constant size subspace state, and then your program is going to be all on a classical computer. So I think it's kind of a nice feature of it. Another thing is, naively, like if I want to send you a token for the program, I need to send you, the qubits that specify my subspace state. But if you use remote state preparation, then you could, in principle, avoid that. You could just have so that like the software owner doesn't even need to have a quantum computer. Of course, this would come at the cost of dramatically increasing the required computation. But yeah. Okay. So now let me get back to the security of our construction. So I wrote security in quotes here because I'm going to show you a security game that's not really that satisfying from a cryptography point of view. And I think the reason is it's very difficult to actually formally specify the right definition of a one-time program. So we're just going to try to give like a starting point that I think intuitively captures some of like what you're at least the basics of what you want. Okay. So the challenger is going to just send, I wrote, p hat in a box. So the challenger is going to give oracle access to the program we saw on the previous slide to the adversary, as well as just a one-time authentication token. Now the adversary first has to just, run the program once. So that means providing an input X and a signature Z, that the challenger can then plug into the program. Okay. Now, if it fails to, evaluate, like if Z is not a valid signature for X, then the challenger is going to abort, and adversary is going to lose. Otherwise, the challenger is going to measure the output of this program and then return it to the adversary. Okay. And then the game ends with the adversary providing a second such, input signature pair. So in the challenger does the same thing. So the adversary wins if they got two different outputs, right? Which in particular means they had to provide two different inputs that both were like valid openings for the program. Okay. So I think this sort of, you can see where this kind of captures what we're going for with, at least intuitively, with one-time program, right? Because it's like this is the adversary running the program once, and then this is like the adversary trying to run it again. We're saying you can't do it twice. You can only do it once. At least if you measure the output. Okay. So so to see for our analysis of this, it's really going to focus in on just this part. What we're going to show is that if the challenger measures this output Y, then it actually is going to collapse the input X and the signature Z to some basis state. It's going to they effectively might as well have measured the inputs, at least from the perspective of any computationally bounded adversary. And then that's going to reduce the security to the security of the one-time authentication. Okay, so I'll say a little bit more in the next slide about this. Okay, so the main technical result is going to be, we're going to show that actually if you have any function f, where for every input w, there's high min entropy over the choice of the randomness, then the function which takes the input w and then it maps it to f of w and using the randomness, using the hash of the input as the randomness, is a collapsing hash function. So what we mean by this, if you measure this output, then it effectively collapses w, at least from the perspective of a computationally bounded adversary. Okay, so if we have this key lemma, then it's going to follow that this p hat is collapsing, at least in the case where the adversary succeeds, where it doesn't abort, and then and then that's going to imply that we can reduce to the security of the one-time authentication scheme, right? Because basically after this, the first time the challenger measures the output, it collapses the signature and the message. Therefore, you have those. So if the adversary was able to get the program to open again, that would mean producing a second authentication. Okay. So so the key, I guess we're not going to get into the technical details of how we prove this. I just want to say the key, the technique that we use for this is this compressed oracle technique of Zandri's. So and I think it's kind of a nice result on its own also, like independently of even this application. Okay, so the last thing I wanted to, okay, I added it last night or this morning, but there's so there's a new paper there's a concurrent work with this work called One-Time Programs Revisited. And this has the same construction as ours essentially, but they go much more in depth into actually defining what security means for one-time programs. So if you're interested in understanding what security should mean for one-time programs with a more sophisticated definition than the one that I proposed, you should totally take a look at this paper. Quantum one-time programs revisited also. So thanks.
Okay, we have plenty of time for questions.
Can you say more what you mean by high min entropy? Be more precise about it?
Yes. Yeah. Great. So what I mean is, so I just said high min entropy here. What I mean is lambda bits. So basically the advantage in winning the game I described is going to be exponentially small in the number of bits of min entropy here. Yeah. So in particular, as long as you have exponentially many solutions to your optimization problem, or exponentially many possible images to get from your whatever it is, then you're fine. Yeah, yeah, sure, yeah. And I guess another question you could start to think about, like, what if it is like small, but it's then like do you get partial advantage? And I think that's interesting. But that actually is addressed, I think, pretty well in this other paper where they introduce this like in definition that kind of accounts for that as well. Yeah.
So I guess about the function f, I was wondering how much of a restriction is it that f has high min entropy, or is there some sort of generic way to convert functions into other functions, like a compiler that transforms it into one with high min entropy?
Yeah. So that's a great question. So really, I think what it is okay. So it's kind of hiding in this security game, I guess. So I guess what you're saying is, okay, I could take any deterministic function, and then I could just say, well, I'm going to make it randomized by outputting a bunch of random bits after the actual answer, right? And now it's a high entropy function, right? Why does that not make it possible to one-time predict everything? And of course, the reason is Alice could just ignore all the rest of the bits. Like the user could just pretend like those aren't there, measure the first part, right? So really, when we're talking about like what you're protecting, what is this F? We need to think about like what is it that the adversary is actually interested in? So if the adversary, if the game was to measure this, if we viewed y as like the actual answer plus this, bogus bits, then like then yeah, you could make anything collapsing, but it wouldn't be like the right game, right? Like really, you have to define f to be the function that the adversary is actually interested in, and if you do that, then this trick won't work, right? Hopefully that was yeah.
How necessary do you think the idealized models are? Do you see a way to remove them from your construction? And also for specifically the key lemma, do you think a random oracle is necessary, or do you think it will also hold for like a collapsing hash function or like a pairwise independent hash function or something like this?
You're saying, do I think that for functions that are sorry, okay, so for protecting general functions, I don't see any way at all of getting rid of the oracle. For specific classes of functions, it seems plausible. I guess is that what you meant by like maybe if this function f is like has some collapsing properties already, then you're saying maybe H. Oh, sorry.
Yeah, H.
Sorry. Well, okay. Well, I said H was I'm modeling it as a random oracle, but since all of this is under an obfuscation anyway, we might as well make it a PRF, right? Because we're only using black box access to H because because P is just going to is under a black box oracle. So actually, this is like you could just think of this as a PRF. And does it work for this too? Well, it has to have some cryptographic properties because this is going to be a computational thing. This isn't going to be true against it's not going to be statistically collapsing, right? It has to be like because it's not injective. That would just mean it's I mean maybe for high enough entropy it could then maybe two wise. Yeah. No, this is a good question. Yeah, so our proof, we had to use like compressed oracles. So I don't see how the techniques would extend, but it's a good question whether you could replace H with like, yeah, something much weaker. Yeah, maybe not even using a PRF. That would be cool. Yeah, then the key would be, I mean, this would all be generated by like Bob, like whoever's, sampling, whoever owns the program, right, has to like do the obfuscation. So whoever does the obfuscation would just use a PRF here and hardwire the key. Yeah. So yeah, so I guess the question, it is like it would at best get rid of the one-way functions part. So it's not, but.
And I guess like, well, a theory question, I guess if can you do something with IO? You would need a lot of gymnastics, like because especially with PRFs, we know that there is no VBB obfuscation of PRFs. I mean, let alone random oracles.
Yeah.
Any hope to do IO?
That's a great question. Yeah, I honestly have no idea. I don't think I should even say. One thing I will say is that this definition that we gave actually doesn't even make sense without black box obfuscation, right? So this is like I required that the adversary submits these
X's and Z's, and then the adversary is measuring, right? We're kind of relying on the fact that the adversary can only query this thing via the challenger. Right, like in particular, okay, if I had a function, yeah, actually, maybe I should go offline for this. I was going to say something that's kind of complicated.
Cool.
Okay, if there's no further questions, or we can take the discussion offline. Let's thank all the speakers in this session for their wonderful talks.